Hi everyone. Topic of this presentation is the nonlinear climate response to CO2 and aerosol forcing for decadal climate simulations. The objective and motivation of this study is to understand the influence of CO2 and aerosol forcing on transient climate, which is critical for seasonal to decadal climate predictions. The general consensus is that the global mean surface temperature response to CO2 forcing is linear. The aim of this study to further understand if there is a nonlinear effect of different levels of CO2 forcing on a global, regional, seasonal, transient climate. A combination of a better atmospheric and oceanic initialization of climate model and predictability from CO2 and aerosol forcing can significantly improve seasonal to decadal climate prediction. Here we have Northern Hemisphere high latitude 55° north to 90° north mean DJF stratospheric temperature from reanalysis dataset. The thick black line shows average of three reanalysis dataset. Now from year 1992 to 2000, there is a positive stratospheric temperature trend, whereas a negative trend exists from 2000 to year 2020. The opposing trend in these two periods is interesting as the general expectation is with CO2 increase, the temperature decreases in the stratosphere, which we see in the year 2000 to year 2020 period. The detrended standard deviation of this temperature also shows the internal variability of the temperature also increases in the second period. Now, this opposing trend can be due to internal variability, such as low-frequency SST modes. Um, the Interdecadal Pacific Oscillation, or IPO, is also known to influence the global mean surface temperature trend on decadal timescale. It can be also due to external forcing, such as CO2 and aerosol forcing, that can also be responsible for this phenomena. To understand this opposing trend in the Northern Hemisphere DJF highlighted a stratospheric temperature trend, we used 1-degree configuration of GOS MITGCM coupled ocean atmosphere general circulation model. A 10-member ensemble of 1992 to 2020 transient or historical climate simulations were performed, where the external forcing was as in observations. Then we ran three perpetually ran control experiment with 30 ensembles each at C1992, C2000, and C2020, where these experiments only had that specific year's external forcing. This is Northern Hemisphere DJF stratospheric temperature mean from our 10-member ensemble mean GEOS MITGCM coupled model historical experiment from the same period. We can see our historical simulation clearly simulates the opposing trend of the stratospheric temperature. There is positive trend in the first period from 1990 to 2000, whereas the negative trend in the second period exists from 2000 to 2020. Now these lines are from our perpetually run control experiment simulations, where orange line is for 30 ensemble mean DJF Northern Hemisphere stratospheric temperature for year 1992. The red on the top for year 2000 and the brown line near orange line in the bottom is for year 2020. Our perpetually run control experiments are forced with only that specific year's CO2 and aerosol forcings and coupled with ocean model that ran with random initial conditions. This perpetual experiment show with only CO2 and aerosol forcing is driving the upward positive trend from year 1992 to 2000, and also the downtrend from year 2000 to 2020. As the ocean is coupled to ran from different initial conditions for these experiments, the low frequency SST modes shouldn't have any influence on this decadal trend that are we seeing here. Now, if this opposing trend is due to only CO2 and aerosol forcing, we should see something similar in the CMIP model's historical run with external forcing. To test this hypothesis, we analyzed 18 CMIP6 multi-models historical simulation, and we didn't see this opposing trend that we are seeing here in this model. However, when you looked at NASA GASE high top historical model simulation from CMF6 that has explicitly resolved stratosphere, we found the same opposing trend lines in these periods, shown here in the light gray lines. So we think the model that correctly simulates stratosphere circulation produces these responses due to CO2 forcing. Here we have zonal mean DJF temperature in log scale for perpetually run control experiments for year 1992, year 2000, and year 2020 on top panels. In the bottom left, we have 30 ensemble member difference between C2000 minus C1992, and bottom middle panel plot shows C2 2020 minus C2000. Clearly, we can see Northern Hemisphere stratospheric temperature increases from 1990 to 2000, whereas it decreases from year 2000 to 2020. The stippling shows the significant grid points in the figure. Here we have figures from perpetual run experiments, same as last slide, for long wave cooling. In the bottom panel, we see the long wave cooling response is consistent with temperature, that the long wave cooling decreases with temperature increase in the first period from year 1992 to 2000, whereas long wave cooling increases with temperature decrease in the second period from year 2000 to 2020. Now, similar plots for transient wave activity that is responsible for heat transfer from tropics to pole and shows that the heat propagation in the northern hemisphere high latitude stratosphere increases in the year 1992 to 2000, whereas it decreases from year 2000 to 2020. This dynamical forcing from transient eddy motion shows the role of dynamical forcing is settling the warming part of the pattern. In summary, our 10-member ensemble mean transient run experiments forced with variable CO2 and aerosol levels produces northern hemisphere DJF stratospheric temperature trend phases very similar to reanalysis. In the first period, the northern hemisphere DJF temperature increases, whereas it decreases in the second period. Our perpetually ran coupled control experiments that was forced with specific years of aerosol and CO2 forcing also produces a very similar temperature trend. The presence of this pattern in the perpetually run control experiment suggests that it is the external forcing and not low frequency variability that is crucial for this phenomenon. The long wave cooling response to CO2 and aerosol forcing in this period also consistent with temperature change, that long wave cooling decreases in the first period of 1990 to 2000, whereas it increases in year 2000 to 2020. The dynamical forcing from transient eddy motion show that the heat transfer due to transient wave activity increases in the year 1990 to 2000 and decreases the year 2000 to 2020 that drives the northern hemisphere DJF stratospheric temperature response. Preliminary examination of CMIP6 historical simulations in general show no sign of warming due to eddy transport of heat poleward. However, the CMIP6 contribution from model with an explicitly resolved stratosphere do show the separation between the two trend regimes that we see in reanalysis and GUS MITGCM simulation shown in here. Our next steps would be to investigate potential heating sources that triggers the wave activity that leads to responses in the polar heat transport under different levels of CO2. Separating the influence of CO2 and aerosol forcing on northern hemisphere DJF stratospheric temperature trend would be also interesting to look at. Thank you.